So hi everyone. So welcome to a special lecture. If you're familiar with our programs here, you know we usually have TriStar in the spring. We have the Stellar Society lecture in the spring. We have the Joe Klein lecture usually in September. This is a special event tonight that actually came to be because the local section of the American Chemical Society, Kent Kabler contacted me and said, you know, our group likes to come out to events. What have you got coming up? And I said, let's just make an event especially for y'all. And so we've partnered with them and our usual suspects, the GTCC Foundation, the Stellar Society, and all our volunteers to put together tonight's talk. And because we're working with a chemist, so the audience, Anthony is going to be thick with chemists tonight, so just be prepared. We tried to pick out something that had nice overlap with astronomy and chemistry, and Don Klein, who's always in the front row at these talks, suggested that the person to ask is Anthony Love from Appalachian State, and we thought, well, what a great idea. And we know Anthony from his meteorite work, and he was happy to join in. And so we have this event tonight. So thank you all for helping put this together. And as always, thanks to the Martin family and the Klein family for making our whole program possible. Aaron Martin's vision of the observatory, and then Don Klein working with him to make it happen. We opened our doors in 1997. And so we've been doing this for a lot of years, and we plan to keep doing it. And so if this is your first time coming out to one of our events, we hope you'll come to many more. Like I say, we have a regular schedule of these. If you're not in touch with us about getting on mailing lists and such, see me at the end. I'll tell you how you can do that. Also, many of you know there's a solar eclipse coming along this weekend, and are you aware of the weather forecast for tomorrow? So we had great plans to set up a battery of safe solar filtered telescopes in the parking lot just out above the building here on Saturday. My expectation is that session is not really going to happen, just because of the weather. I've been talking with local meteorologists, checking all the models, and it looks like we're not going to be able to observe the sun, except perhaps it might peek out through the clouds in mid-afternoon, right about as the eclipse is ending. Go figure. So officially, I think we're going to actually cancel that event, but if things improve, we've got a few people on call that will come out and try to set up a telescope or two. So the other option is if it does clear off a little bit and you can see the sun peeking through the clouds and want to look at the eclipse, we have solar eclipse classes. And in fact, Kelly Sayers will be out in the lobby at a table where you can obtain a pair of solar eclipse glasses, or also viewers, little cards, for your generous gift of $2 to the Klein Observatory to support our outreach programs. And you'll get one of these in appreciation. So if you'd like to, just in case the eclipse is visible, want to observe it safely from wherever you are, make sure you get one of our observatory viewers. And conveniently, they say on there when we're open to the public for looking at telescopes at night, and that is every Friday night, as long as the skies are clear. And so I noticed that most of you brought clouds in with you tonight, so please don't do that when you come over here on Friday nights. We will assess the state of the sky at the close of the talk. If it is reasonably clear, we'll open the observatory and we can show you how to get there afterwards if you don't know where we are. So during the Q&A session, some of our volunteer hosts will be checking the sky and they'll give us the signal, and I'll announce that. So if we do get to observe tonight, come out and look through the telescopes. If not, come out on another Friday night. We're open all year long. The time we start actually changes because the time it gets dark changes. But coming up very soon, there's the time change, and once we get into November, we start at 7 until March comes, and then we start a little bit after darkness is falling. And so there's a rotating schedule. We have a website that has that. So if you haven't been out to the observatory, come on out. Again, thanks to our volunteers. They're going to help out. I see a few of them there in our front rows tonight. They come out lots of Fridays and they enjoy sharing the universe with you. So come and see us and look to our telescopes and find out what you're looking at. So enough about that. Tonight we have a very cool topic. Like I said, we have Anthony Love from Appalachian State University. You might remember that we had someone from the other ASU here just a couple of weeks ago to give a talk about the JWST, but now we have the real ASU, I guess, with Anthony, who sort of runs their research labs in the geology department, and he's in the last decade and a half or so, he's gotten really interested in meteorites and in testing meteorites and figuring them out. And what he's going to share with us tonight is sort of how we use that kind of information to figure out the history of the solar system. And you might have noticed that there's even been some news about something related to that just this past week, and perhaps he'll touch on that. So let me turn things over to Anthony Love, and let's get the program underway.
Now, please don't blame me for the clouds. I come from Boone. There's never clouds in Boone. But thank you so much for having me. I'm really excited to be here. As Tom said, I'm Anthony. I'm from the Appalachian State University, the one in Boone. I became interested in meteorites in 2007, and I had the good fortune to meet Don Klein and get to examine his incredible collection. After that, I started to recognize I had the skill set, the access to instrumentation, and the experience to classify meteorites. So since 2009, I've been classifying desert meteorites that come from the Sahara Desert, prominently in North Africa. So at Appalachian, I am the research operations manager, so I take care of our class's collections assets. But for my research, I'm doing prominently meteorite classification. Classification is kind of the backbone work of planetary science, where we're describing the features of rocks that we observe, as well as measuring the chemical compositions that allow us to place certain types of meteorites within the known classes of samples that we have. Over the years, I've been lucky enough to collaborate with Don and the Pisgah Astronomical Research Institute to work on some of their collections, as well as collaborate with some of the top planetary scientists in the United States. But what I'm excited about sharing with you tonight is how minerals marry geology and chemistry to the idea of learning about the early history of the solar system. Maybe. There it goes. So in order to achieve this goal, we have to recognize what the first solids are that form in our solar system. They are composed of minerals, and we want to know how those minerals go together into forming rocks that eventually accrete into asteroids and larger planetary bodies. We're interested in where in the solar system this is happening with reference to proximity to our sun, and we also want to know what kinds of changes rocks are experiencing on these parent bodies that tell us about the active processes that make up the evolution of bodies in our solar system. Ideally, we want to be able to match meteorites to their parent body asteroids or or planets. And in some cases, that's really easy to do. In others, not so much, because the bodies may have been completely disrupted or destroyed. And then finally, we're interested in the chronology or the time frame of events that these things happen. So we have kind of the rationale of what we're doing. We need to know what a mineral is. We're going to talk about a group of rocks called chondrites because these are the rocks that have undergone the least amount of geologic change over the history of our solar system. We're going to talk about the evidence we have for water being involved in these rocks and their changes, as well as the occurrence of organic molecules that occur in a great diversity in many types of carbonaceous chondrite rocks. And then how all of these aspects are relevant to the most recent exploration of the asteroid Bennu. So a mineral is a solid, naturally occurring substance that has a well-defined chemical composition that's organized into a crystalline structure. Some examples that are very common here on Earth, but also on meteorites, are silicate minerals like pyroxenes, olivines, silicon carbide, which is also known as carborundum, the hexagonal form of water when it's cold enough, and serpentine, which is also known by its nastier name, asbestos, and then finally good old table salt. So to understand what minerals can tell us about these processes and origins, we have to know what they're composed of. Minerals contain major elements that give them their chemical identity, and that's some of the information that tells us more about the identity of the rocks and how they formed. Minerals also contain minor elements that occur in lower abundances and trace elements. And these can tell us something about the activity of processes, but also give us a sense of sources from which the minerals originally formed. And then finally, we have isotopes, stable isotopes of elements like oxygen, and then radiogenic or radioactively decaying isotopes like these listed here, the manganese chromium system, aluminum, magnesium, and uranium lead that we use to give us a sense of timing of when events happened. So just as an example with major elements, pyroxene is the name given to a family of minerals, and you can see here that there's actually a lot of compositional diversity depending on the amounts of calcium, magnesium, and iron that you have. They create different forms of the mineral. And this is important because when we're looking at meteorites, as you can see in the graph on the left, certain compositions of pyroxene are very diagnostic of certain types of meteorites. So to understand how these first solids are forming, we need to look at rocks that contain minerals that have never changed since an asteroid originally accreted and the minerals formed. So to do that, we look at a group of rocks called the chondrites, specifically carbonaceous chondrites. Now this is a photograph of a slice of rock that's 30 microns thick. We glue slices of rock to a glass slide and we can observe the minerals under a polarizing light microscope, but we can also put them in instruments like scanning electron microscopes to study their chemical compositions. Now, the first part of this rock that we're going to talk about are these irregular shaped objects that you see pointed to by the yellow arrows. These are called CAIs. CAI stands for calcium aluminum rich inclusions. And we can see by the list of minerals that we find in them, most of these minerals are enriched in those elements. We've also got some other high temperature elements like scandium and zirconium that make up some of the minerals within these inclusions. You can see from this graph or this chart here over on the right, these cations, when they form oxide compounds, generally have very high melting or crystallizing temperatures. So the image on the right shows what's called a false color X-ray map. We use X-rays to map out the distribution of elements within minerals. Here we're looking at minerals that are composed of iron, calcium, aluminum, and magnesium. What we can see in that image, if I get my laser pointer, this object here is one of these CAIs. We can see that it's composed of interlocking crystals, and that tells us that this grew from a molten state. We can also see that it's composed of layers of minerals. Now this chart here over on the left is a chart that shows us the sequence of minerals that are expected to form from a cooling gas that has the same chemical composition as our sun. And when we study the compositions of these minerals in CAIs, those are indeed the first minerals that we find to condense in a cooling gas. And we see that that predominantly happens at higher temperatures. Now you've heard the old joke that geologists are the only ones who will date rocks. Well, it's true. And calcium aluminum inclusions have been consistently dated as the oldest or very first solids that have formed in our solar system. The oldest one, I believe, comes from a rock called Efremovka, and it's been dated to this date 4.586 billion years. So the next object in these rocks that's of the great scientific curiosity are these objects, chondrules. These objects have been studied since the 1800s, and as of 2023, we still don't agree on how they formed. Now, chondrules are spherical objects that have crystalline textures that showed us they crystallized from a molten droplet. So when we look at examples of these, we can see them in light microscopes, but here we've got an image from a scanning electron microscope called a backscattered electron image. What we're seeing is the crystal structure of these olivine crystals that are the vertical bars surrounded by this rim of olivine crystals. Olivine and pyroxene make up 95% of the minerals that we see in all meteorites. This is another type of image called a cathodoluminescence image, but for brevity, we just call them CL images. We form these when we're bombarding a sample with an electron beam, and in turn, elements within the sample get excited and give off visible light in the form of cathodoluminescence. In this case, we're looking at another one of these olivine chondrules. So the olivine are the red crystals, and we notice that some of them have these concentric rings of color that show us how these crystals grew and changed composition as they were growing. We also have this dark yellow area that we call mesostasis. And mesostasis is really the name of a material that's left over, that's composed of all the elements after we used up all the magnesium, iron, and silicon to make the olivine. In addition to elements like aluminum, silicon, calcium, we get volatile elements like sodium, potassium, and sulfur. And so when we see these two features within a sample that grew from a melt, we knew that that melt had to crystallize very rapidly, because if you hold these at higher heat, those zoning features disappear and we evaporate off all these volatile elements. So in thinking about how these objects form in space, we need to think of some process that forms a whole lot of them. It's estimated that there's about 1 trillion megatons of chondrules that make up the asteroids in the asteroid belt. And of those asteroids, we believe we have rocks that indicate there's 16 different types of asteroids that we've sampled with meteorites. Of those asteroids containing chondrules, all the chondrules are composed of those two minerals, olivine and pyroxene. So that tells us something else. It's really important that our precursors to form these melted chondrules have to have similar compositions. Now we're going back to that diagram that shows how minerals condense from a gas. And we can see where the CAIs are, that they form at these higher temperatures. And then the next minerals to form are the exact same suite of minerals that we find making up the phenocrysts and the chondrules, like the olivine and pyroxene, and then the minerals that make up the mesostasis, these different varieties of the mineral plagioclase feldspar. So we recognize that these are forming, again, at a lower temperature, but we have to recognize the fact that this is a slow, gradual process of cooling. And with that slow process, we're not able to form those chondrules, so we're just forming precursors that would be melted later. So by far and away, the most efficient and repetitive process that affects bodies in our solar system is the activity of impacts. They have the capability to produce very high temperature melting very quickly. And when we splash molten material out into space, we have a mechanism to form rapid cooling. And then, as I said, this happens over and over again. For an example of that, look at the surface of the moon. The next aspect of these rocks that we're interested in is the stuff that occurs in between the chondrules and the CAIs. This is simply called matrix, and it's composed of a mixture of very fine-grained, iron-rich varieties of those same minerals, olivine and pyroxene. But they also contain these objects' presolar grains. Now, presolar grains, as their name suggests, are relics from other stars. During the first chemical studies of carbonaceous chondrites, they recognized that they contain isotopic anomalies of exotic elements like xenon and neon. The way they found the source of the xenon and neon is a group from the University of Chicago working with Ed Anders actually took samples of the meteorites and digested them in very strong acids to get a residue that was insoluble in the acid. And that residue actually turned out to be thousands of tiny microscopic diamonds that had that isotopic signature of xenon. Now today, we try to use some more gentle methods. We use an instrument called a secondary ion mass spectrometer, and we can measure the isotopic ratios of elements like oxygen to help us identify these grains in situ. So we can put a slice of rock in this instrument, vacuum it down, shoot it with the cesium beam, and get isotopic information that also gives us context with the other minerals that surround it. Now we have lots of different types of minerals that make up these presolar grains. Silicon nitrides, I already mentioned the diamonds. We've got an abundance of different types of carbide minerals. But perhaps the most common ones are silicon carbide. In this graph, we're looking at the isotopic recipe of different silicon carbide grains from the same meteorite. And what we can see is there's different populations of grains based on this chemical recipe of isotopes. Those populations gain their isotopic signatures based on the process that star is engaged in throughout its lifetime. With the blue squares, we're looking at a group called the mainstream grains that are produced during the CNO cycle within large asymptotic giant branch stars. Within these blue triangles, they're more enriched in the heavier element of nitrogen, and they show the signature of supernovas. So here's another example of geologists dating rocks. Philip Heck from the Chicago Field Museum did a study where they had isolated some of these presolar grains, and he used neon isotopes to date when they formed and found that some populations of presolar grains formed around the same time as those calcium aluminum rich inclusions, and others formed about 3 billion years before. Now you're going to hear me talk about dating relative to the formation of calcium aluminum rich inclusions a lot tonight, because those inclusions we're able to date those using uranium lead dating, which gives us an absolute time when it formed. A lot of our other minerals within some of the components of meteorites don't contain radiogenic isotopes like uranium or lead, and so we have to date them using relative dating systems with other isotopes that we can correlate. So everything's going to be related to the formation of CAIs. And it makes sense because those are our first solids that we formed. So what we see from examining minerals within chondrites is that CAIs were definitively the first solids to form, and they formed from a cooling gas that has the same composition of the sun. We see that chondrules formed just a little bit later, or at least their precursors did, and possibly through the activity of impacts between bodies. We can see that presolar grains predate the formation of CAIs and chondrules and originate on the basis of activity from other stars. And we also know, I didn't talk much about this, but the matrix materials that include the presolar grains show evidence of not having ever changed in their lifespan. By the fact that we have the signatures that we do from presolar grains, chondrules, and CAIs points to the fact that these rocks have never changed since they first formed. They've never experienced any significant geologic processing. So we're looking at the right materials to look at origins of solar system materials. So we're not only interested in what happened to form the rocks, we want to know something about geologic change that's occurring on these bodies. With carbonaceous chondrites, we're most interested in looking at how ice changes to water and what it does to the rocks. Typically, we start with a dry asteroid, and if we have some source of heating, we can form water that creates a muddy, soupy mix that starts to change the nature of the rocks. Excuse me. And that occurs from the radioactive decay of isotopes like iron and aluminum. So here we're looking at two backscattered electron images of these objects' chondrules. This one is from an ostensibly dry asteroid called an ordinary chondrite, and this one on the right comes from one of these carbonaceous chondrites. This one is an example from what we call a CM2, which is a very hydrated rock. We can tell by comparing the two images, this one looks like it's really been broken down, and that's showing that process of hydration. We're destroying these beautiful olivine crystals by eroding the edges. They've been cross-cut by veins. All the mesostasis material in between the phenocryst has been transformed into this phyllosilicate mineral that is a serpentine. And we can see the addition of that water in the chemical formula. Now we know this process happens at relatively low temperatures because we haven't lost the chemical zonation that has to be retained during the low temperatures. We also see the appearance of other mineral phases that show they've been altered by aqueous fluids and oxidized. In most stony meteorites, we find metal grains composed of iron-nickel alloys. If we subject those to some oxidation reactions during hydration, we form the mineral magnetite. We can also form precipitate minerals like gypsum and calcite. Again, we can use that relative age dating technique using the manganese chromium system that indicates that this process happened between 1 and 12 million years after the formation of CAIs, and it persisted for about 12.5 million years. Now, we know that water can change asteroids while water is on that planet, but we also have some information about water being delivered to ostensibly dry asteroids. So this good-looking group of 6 boys were some of the rare humans to watch a meteorite land. Not just see it come through the atmosphere, but actually observe the spot on the ground where it fell. This happened in Monahans, Texas on March 22nd, 1998. Equally rare was that they're in a place that's close enough to get a NASA geologist who studies meteorites there in 2 days before it rained. So what's important about that is they get to pick up samples before they get contaminated by anything. Now, when they process the samples, they recognize the rock is a very common type of meteorite called an ordinary chondrite, but it contained these extraordinary features of pockets that were filled with these purplish, bluish crystals of excuse me, sodium and potassium salts, halite and sylvite. These are minerals that precipitate from a fluid. In that same year, in the Zag Mountains of Morocco, we observed the fall of the Zag meteorite that also contained the same halite inclusions. This one was different, that it actually has these cavities which are filled with some of that original brine from which those halite crystals formed. Not too long ago in 2020, this meteorite, the Sidi El Habib meteorite, fell in Morocco, and they cut it open and saw again the existence of these blue halite crystals. Now, in this instance, the halite was actually a replacement mineral, replacing some of the minerals already in the sample, like the sodium feldspar and the chlorine-rich variety of the mineral apatite. So in one case, we have water being delivered to a dry asteroid. In another case, we have water that's actually present on the asteroid, altering minerals and replacing them. So we have evidence that water existed on these bodies early in the solar system's history. We also see evidence of water altering these rocks more recently. Scientists from Macquarie University in Sydney, Australia, and Florida State University were examining alteration processes that occur in these carbonaceous chondrites from the perspective of uranium isotopes. What they're doing is looking for 2 of the nuclides in the decay chain of uranium-238, uranium-234 that is a fluid mobile isotope, and then thorium-230 that is an immobile isotope. What they found when they studied these carbonaceous chondrites is that they had enrichments of the mobile isotope uranium-234. In some cases, they had 5 times as much of the 234 isotope as the 230. What's important about that is that both of these isotopes have nearly the same rate of decay. With reference to the span of geologic time, they decay almost at the same rate. So when we see enrichments in these rocks, it shows us that there was some fluid process that transported that uranium isotope and deposited it in minerals. Now, most of these carbonaceous chondrite rocks show cosmic ray exposure ages that say it's been less than 1 million years since they've been blasted off the surface of their parent asteroids. And so these isotopes have long enough decay rates to show us that there's still a lot of parent isotope left, which demonstrates that this process is happening relatively recently, again, with reference to the span of geologic time. So the only thing that we have to know, we know that the isotope is mobile, and if these rocks are out in space, the fluid can't be liquid, it's got to be a solid, it's got to be ice. So we just need some source of heat to be able to explain why we have these isotope enrichments. The ways we can heat these rocks in space are by making a transit around the sun as they're getting close to the orbit of Earth. We can do it by the process of ablation as that rock is actually entering the atmosphere and heating up. Or we can do it through impact with the surface of the Earth, where all that kinetic energy gets transferred to between the crust and the meteorite itself. So the evidence we have from minerals about water is that hydrate minerals indicate that there's low temperature hydrothermal alteration of some of the carbonaceous chondrites. And this occurred while those rocks were part of their parent body asteroid, and it happened between 1 and 12 million years after the formation of those first solids. We have precipitate minerals that occur on ostensibly dry asteroids, and they show us that water can be present or delivered to different bodies. We know that ice was the likely source of the water, so we have implications for some source of internal heating, which in most cases, when we're talking about asteroids, we're talking about the heat delivered by radioactive decay of an isotope of aluminum, aluminum-26. And then finally, we have evidence that there was ice that continued to accrete to some of these bodies even after they were liberated from their parent asteroid and delivered to Earth, where that ice could melt and mobilize uranium isotopes. So we also see ample evidence for organic molecules. This is nothing new. We had the Murchison meteorite fall in 1969, and since the 70s, we've seen close to 15,000 different species of organic molecules. These are pictures from the press conference on Wednesday of a carbonaceous compound. They didn't really say what it is, but it looks like a mixture of graphite and other grains in reflected light. And then this is a UV fluorescence image. And under UV, carbon compounds glow. So the bright spots are organic rich molecules that they call organic globules. And those are the actual physical species of particle that gives us the most information about the types of organic molecules we're looking at. Now, the spoiler alert is these are not minerals because they do not have crystalline structures. They have incredible molecular structures, but they're not organized in those repeating fashions like we find in crystals. So we know that meteorites contain a huge inventory of both soluble molecular compounds as well as insoluble macromolecular compounds. Think huge molecules. Over the years, we've found things like nucleobases for all the parts of the DNA chain in meteorites. In these organic particles, we found a number of different amino acid compounds, sugars, phosphorus compounds, as well as alcohol compounds. Now, in 2020, Japanese scientists found a compound known as methamine, or hexamethylene tetramine, which is thought to be one of the compounds that breaks down into formaldehyde and ammonia. These are really important compounds in assessing diversity of molecular chemistry because we can form all of these different structures of molecules by some process that affects these molecules to rearrange them. So back to the Monaghan's meteorite and its salts. Mike Zielinski and a scientist named Queenie Chan discovered that by dissolving some of these halite crystals, they had some of those organic globules trapped within them. So we have a mineral that precipitates from a fluid that had actually trapped some of these organic molecules. Now, the rocks that these occurred in are known as breccias. They're rocks that are broken up and composed of many different types of pieces of meteorites. Sometimes it's all the same meteorite. Sometimes there are other types of meteorites hosted within the breccia. In this case, the Zag meteorite had pieces of other carbonaceous chondrites mixed in. And when they studied the organic globules within the halide and compared it with the organics that they found in the carbonaceous chondrite class, they saw that there's actually two different inventories of organic molecules. So that implies that we're sampling organic molecules from two different sources on the same asteroid, which was ostensibly dry when it first formed. So what we learned from the organic molecules is both soluble and insoluble types make up this huge diversity. Again, 15,000 different types of organic compounds that occur in most of the types of undifferentiated meteorites, those that are coming from asteroids that have never experienced change. We find that many of life's precursor molecules have been detected in these meteorites. And we see that there's a method that we can deliver organic molecules to other bodies in space. Similar story with water. Now, with respect to this halite from the Zag and Monaghan's meteorite, we can actually look at other geologic aspects of that asteroid to start to constrain when those organic molecules and salts were delivered to that asteroid. So we learn a lot from the studying minerals within chondrites. We learn about the nebular origins of the different solids that make up these rocks. We learn something about the types of geologic processes involved, as well as the time frame that these processes are acting upon. We learn about the presence of water and how it affects these rocks, and the timing of when those effects happen, and the possibility that we can deliver water as well as organics to other bodies. So all of this goes into what planetary science has been saying for decades is we have the capacity to deliver both water and prebiotic molecules to other bodies. And perhaps that's what gives us the possibility of delivering water and life to Earth. And that's where we come back to Bennu. That's the whole point of this mission, is to help us understand the origins of our solar system, how things have formed, how we've delivered possibly water and prebiotic organic molecules to other bodies. So we chose Bennu because it is a carbonaceous asteroid, or at least we thought it was based on spectroscopy. When they showed SEM photos from preliminary studies of these particles that they just uncovered last week or this week, they saw that they contain those serpentine minerals. You can see they look like these wavy, snaky forms, and that's where the mineral gets its name. So those are those water-bearing minerals. They saw that they contain these crystals that we call framboidal masses. If we're looking at them with a really good electron microscope, they look like little circles. This is a transmission electron microscope that's showing that they have more of a geometric habit. They also showed sulfides, another form of oxide, which is one of the smoking guns that they originally thought was a signature for life that they found in a Martian meteorite back in 1994. Of course, that got debunked, but the important part of it is bacteria do synthesize iron oxide minerals with that form. As I said, they found evidence of carbonaceous material, and in fact, it's more carbon rich than any other known carbonaceous chondrite. 4.7 doesn't sound like a lot, but when you're talking about meteorites, it goes a long way. So one of the other reasons we're interested in it, of course, because it is a near-Earth asteroid, and that means it has the possibility of intersecting with Earth's orbit someday. I'm going to graze over that because that's going to happen possibly after we're long and dead. The other more important part is that it's a rubble pile asteroid. At some point in its history, it was completely disrupted and broken up into fragments. Those fragments reaccreted into the body that it is now, but they're held together just by weak gravity. So we want to know, if we have to change the orbital dynamics of that, how do we effectively do it? But for a geologist, rubble piles are cornucopias of rocks because oftentimes they contain evidence of the other impactors that broke them up originally. So we get more observations in something that's broken up because we can get a greater diversity of rock types. So why did we do this mission in the first place? We're interested in engineering and designing a mission that created ways to safely deliver uncontaminated samples back to Earth. We've got another mission in mind to do this very same thing, but from Mars. That's what the Perseverance rover is doing right now, is collecting samples, stashing them so that we can bring them back to Earth someday to study. We chose Bennu because it contains pristine information about ancient and possibly prebiotic organic molecules. It's a carbonaceous asteroid. It has hydrated compounds. We know it has all the right stuff, so we've got the right target. But also, and perhaps more important, most important, is we have a way to store and curate these samples and retain their pristinity for future generations of scientists. Since I became interested in meteorites, there have been many new techniques that have been introduced and more that we've learned that wasn't available when we started. It's likely going to be the case 10, 20, 50 years from now. Just this last year, they opened some of the drive tubes that they collected on the surface of the moon and started studying those with all the new techniques that we've had since the 60s. So there's a world of knowledge waiting to be learned from studying these samples in the future. So thank you to the OSIRIS-REx team. Thank you to you all. And I'm happy to take any questions. Yes, sir. I think they said it was between 60 and 250 grams. What we saw on the outside of this chamber, they haven't opened up the main chamber. And so that looks like, based on the density of this rock, which is really low density, that's probably like 2.5 or 3 grams of material. But for a scientist and what they can do with the instrumentation we have available, the previous mission to an asteroid that the JAXA, the Japanese Space Exploration Agency, sent collected 20 milligrams of material, and there's been a ton of science done with it. Yes?
So you said the
Phenocryst.
radiance inside of the crystal?
It's actually the name of the crystal itself.
Okay.
So this is a phenocryst.
And you said that was proof that it like melted and then crystallized really quickly?
Well, because the shape of the crystal has this geometric outline, that shows that it grew from a liquid with nothing to impede its growth. So it formed a perfect crystal. But in and of itself, that doesn't tell us that it's quick growth. It's those other aspects, like cathodoluminescence, that show us the quick growth. We had some more hands on this side. Yes, sir.
Yeah, I found the isotopes of all these compounds fascinating. But when you're talking high impact collisions or near solar or wind or whatever, aren't you forming all of these odd isotopes? And how do you use that for dating?
Well, that's part of the debate as well, because we have long-lived isotopic systems and short-lived isotopic systems. The ones that we use primarily for dating are aluminum and magnesium. And so that's a short-lived system. So we're studying the daughter products. And so that system doesn't seem to be disturbed, but it relies on the assumption that that isotope is uniformly present throughout our solar system. And we're finding more evidence all the time that that's not the case. So time is still an issue, but the samples, thousands of samples have been analyzed over the decades, and the data is consistent with some of these dates. Yes?
So, back to the still light and that light.
Yeah.
Do you mind going back to that slide for a second?
Oops.
So, these are cross sections of the meteorites, and I assume they're fairly small cross sections, right?
I believe so. These chondrules, I failed to mention this, are millimeter-sized objects.
I thought it would be tiny. Silite and halite, they both have their own crystal structure. Can you see that crystal structure in these photos?
When you have crystals that grow in contact with one another, you can't see the cubic crystal structure as well. Typically, perfect crystals that show that structure are growing in an area where there's nothing else to impede their growth. What we can see is the composition, and if we look at them under a microscope, if they're prepared correctly with no water whatsoever, you can see that it's what we term isotropic. Due to the crystal structure, it refracts light the same in any direction. So we can tell it's got the properties of a cubic mineral, and it's got the composition of a cubic mineral. And so that's what we base our identity on. Does that?
I do have a follow-up question.
Yeah.
To that. The halite crystals have the blue color. You go out to Seals Lake in California, halite forms pink,
Yeah.
and white, but you oftentimes get the much more rare blue color. Do these blue crystals have the same composition as those blue crystals?
Well, halite is halite is halite. What's different about them is that these were likely subjected to cosmic rays while on the meteorite, and it's believed that those cosmic rays are what changed them to that blue color.
Okay, thank you.
Yeah.
Yes, I have a question.
Yes, ma'am.
Did you mention something about maybe having the same composition of a diamond?
Yeah, there's pre-solar grains. Like I was saying, there's a bunch of different types of minerals that show that pre-solar isotopic composition. And the first ones that were formed, or the first ones that were recognized, were diamonds. And the way they found that out is by looking at them with a transmission electron microscope, where you can actually image the atomic structure and how those carbon atoms are arranged. Yes? So in carbonaceous chondrites, these are hydrated rocks, and so we break down those iron nickel metals. But if we have iron nickel metal like we do in iron meteorites, that does contain amounts of elements like gold, silver, copper, phosphorus, gallium, germanium, and so on. There are a whole class of elements that we call siderophile elements that want to form with metals. And so that's one of the ideas about asteroid mining is what are the right sources to go to for some of these elements that we're interested in. Of course, the one that we're most interested in is water, because how are we going to survive to get people further out to examine and figure out how to bring things back?
So these are its impact. And I'm assuming that would run off the water that we're looking for. How does it maintain on that?
Well, if you're in, I mean, currently there are asteroids like Bennu that are happily sitting out there that have been impacted, but there wasn't enough heat in those impacts to burn off or dehydrate the water that's in those minerals. And that therein lies the other problem. How do we get the water out? So what we're interested in finding when we're looking for water is we're really interested in finding ice. And we do see ice around our solar system. We see it on the poles of Mars. Yes?
Why do you have that slide up? Can you explain again the middle picture? What
So
you use to figure out the isotopes?
this is called a secondary ion mass spectrometer. So in mass spectrometers, we're looking at separating isotopes in elements according to their mass, their atomic mass. So we can do that by shooting at a sample with a beam of ions. It's called sputtering. Those give off ions that then in turn go into a tube with big magnets that separate them into their individual species. And so we can use those to look at isotopic ratios of elements we're interested in. Oxygen isotopes are one of the most common ones used in planetary science to give a fingerprint of what asteroid we think something came from, but they also can be used to tell us how meteorites are different from one another.
That's it.
Surely not.
Let me ask you.
Ask away, Tom.
So I found this rock in my yard. I think it's a meteorite. What do I do? Can you tell me if it's a meteorite?
I can likely tell you from pictures what it may be, but in order to legitimately say what an object is, I have to physically see it. I get hundreds of emails a year from people who have found meteorites in their backyard. And a lot of times, the evidence is in the image. And I hate to say this way, but a lot of times people can't take very good pictures of rocks. So that's kind of the first step. If you think you found a meteorite, you can get in touch with me by visiting earth.appstate.edu. My name is listed under the faculty and staff portion, and you can send me an email. We also have a page called Ask a Geologist, where I get asked about meteorites that fall in people's backyards, or gold or diamonds that were found in their backyard. That's the first step, is send me a picture and we'll see if it passes the sniff test. What I'm looking for is rocks that look like they have glassy coatings that show they've entered our Earth's atmosphere. A lot of people think of meteorites as being big, heavy metallic objects. And while some are, the vast majority of meteorites that we have on the surface are actually stony objects. They are composed of those same minerals, olivine and pyroxene. But when they enter our atmosphere, they obtain a glassy coating that is commonly black, but sometimes tan in color. And so I really want to see a good fusion crust. And I really want to see that by a really well-focused picture, not taken in a dark room with somebody's hand sticking next to it, or somebody's dog for scale. Go ahead.
What percentage of
Since 2009, I have identified one meteorite that a guy found in the best place to find meteorites, eBay. This is out of hundreds and hundreds of inquiries. So.
Right, well, let's thank our speaker. If you do have other questions, I'm sure Anthony would be happy to hang around and talk. We do have a few samples of meteorites up here if you want to look at a few. I have word from our volunteers that it is marginally clear, so we might be able to look at one or two things out in the observatory. We don't know how long that will last, but they're going out to explore things further. But if you're interested in going out, we can direct you towards the observatory from the front door here. So just Kelly, Kelly, remember Kelly is out there as an eclipse class resource if you want to get some of those. But thanks again for coming, and an eye on our website for other big events that are coming up. We've got some big things that will be happening in the spring. Thanks again, and thank you, Anthony.
Thank you all.